All right, good afternoon, everybody. Um, Welcome to this afternoon session.
Definitely.
I want to start with the question I asked you to look at on Monday. Did anybody that's here, did any of you complete it?
Yes, sir.
Okay. What answers did you get?
Negative 75.75 for S for the zeros. Negative 70, negative 67.4513 for S1 for the pole. Negative 32.647 plus or minus J 532.369 for S2 and 3. But I don't have the correct right now, but that's what I got.
Okay. Anybody else? Anybody else attempted it?
Yes, sir.
I got the same answers.
Yes, sir. The same answer.
Got the same answers. Okay. No, that's good. That's good. Hmm?
I got something different, sir.
You got something different. Okay.
Yes, sir.
All right. So we have one person not getting the same answers. Mr. Johnson, before we talk about what the answers are, what approach did you take? What method did you use?
Nodal.
Nodal. Okay. Anybody else applied or used Nodal? Is Miss Montague the only one who got something different?
No, sir.
Okay. Okay. Mr. Ramsey are also saying you got something different.
The zeros, I got a number that was close, but I got a different values for the poles.
Okay. Well, the zero. All right. Okay. Okay. And what approach did you take?
The voltage divider.
Voltage divider. Okay. All right. That one can be a little tricky, if you're not careful. So let me be aware. All right. So Mr. Ramsey and Miss Montague. Okay. Well, that's good. Let's just spend a couple of minutes. So, Miss Montague, let's go
Yes,
through
sir.
this. Let's go through this with you and Mr. Ramsey, both of you. You use a voltage divider.
Yes, sir.
Okay. So just walk me through exactly what you have there.
Okay, sir. So I found the capacitor and the branch with the resistor and inductor. I found the sum of those, and I had 4,166.667 divided by S times 25 plus 0.33 S
What you got?
over
What you got for the? Oh, go ahead. 4,000.
4,166. So you wanted the complete
Yeah,
answer?
man. Just tell me what you had there. 4,000 what?
4,166.667
4,166. Okay, 0.667.
divided by times
Mm-hmm.
25 plus 0.33 S. Those brackets all 4,166.667 over S plus open bracket 25 plus 0.33 S.
Okay. And how do you move from there?
Well, I found the answer for that, and I got 4,166.667 times open bracket S plus 75.758 all over S squared plus 75.758 S plus 12,626.26.
All right. All right. I'm sure some numbers there were okay, but one of the things I want to encourage persons to do, especially when you are doing this particular topic, is as much as possible try to stay away from simplifying too quickly. In other words, work as much as possible with the fractions, because usually they will cancel themselves out. All right, so where I would back company with you quite early in the game is where you simplify the 10 to the 6 over 24. Because that's where you got the 4,000, right? So you divided the 1 million by 24.
Yes.
Hmm?
Yes, sir.
Yeah. It would have been a little cleaner if you had just left it as 10 to the 6 over 24s. I'm trying to add some. Let me just control. All right. All right. So if you had just left it as Mr. Rams, it sounds to me that did you also simplify?
Yes, sir.
Okay. Let's add some more to this. All right. So if we had just kept it as 10 to the 6 over 24s. Times 25 plus 0.33 S. Over 10 to the 6 over 24 S plus 25 plus 0.33 S. Yeah? All of that would have simplified to, because once you see this 24S in both the numerator and denominator, it stands to reason that it's going to cancel out, all right? So usually I just leave it there. So you'll end up with 25 times 10 to the 6 plus 0.33 S times 10 to the 6, or 0.33 times 10 to the 6S. That may look a little cleaner. Over 10 to the 6 plus 600S plus, this is not the place that it looks a little messy, all right? So that would have been the parallel. And then from there, you do your voltage divider. Okay? So once you have done your voltage divider, then the results that the others that would come out. So do me a favor. This is for the parallel section. You're now going to divide that to find the voltage across the load, which is VR. Yes. So VR is equal to VS times the parallel section, which of course would be that, over Z parallel plus 15 plus 0.2632 S. All right. So simplify this. All right. Simplify this for VR and check the answers again. All right. So just note the answers. 75.76, and that was for the zeros. And for the poles is 67 minus 67.45. And if you want to call it P2 and 3, it's minus 32.65 plus minus. So there are 3 poles. J5 32.37. All right, so just note those answers.
Excuse me, sir.
Yes.
I think where she went wrong was where she had 4,166.67. It should have been 41,666.67.
Okay. Yes, that's a million divided by 24. Yeah. Thank you. All right, so just double check. But as I said, and I think you're making the point here that we don't want to do those simplifications so early, right? Just as much as you can, just keep your fractions, all right? For those who attempted it using nodal analysis, so Ramsey, Miss Montague, you have this?
Yes, sir.
So here for nodal analysis, you would have VR times 24S over 10 to the 6 plus VR plus VR over 25, sorry, I was a little distracted, plus 0.33S plus VR over 15 plus 0.2632 S, and that is equal to VS over 15 plus 0.263 S. All right. Of course, you have VRs on one side, so you have VR into whatever is in that bracket, and that's equal to VS. So you from that you can find your VR over VS. All right, and you'll get the same result. Okay. So now that we have noted where the arrows were, I'm going to assume that nobody really had any major difficulty we just had some minor calculation errors. Of course, given the structure of the exam, those errors can be rather costly. All right, so let us, let me just, I know that our schedule calls for for a tutorial on this afternoon, but I'm going to move to filters because this will impact your project. Yes, and so we'll have all the next week to wrap up filters and treat with any questions that you may have on both topics. All right, so that's how we're going to proceed today. So we're going to deal with filters, and there's a lot of writing here, so just be prepared for that. Okay, so what are filters? I mean, why do we use them? And I deliberately put this particular topic at the end because it calls upon and it uses a lot of what we have done so far for this module. So filters. Simply put, a filter circuit is one that's going to allow a certain set of signals to your output. Those signals are within the desired frequency range. Okay, so it is what you want to happen within that frequency range, and I'm making desire here being both a positive and a negative, because if your desire is that you're blocking certain frequencies, then that in of itself is acceptable. So your desire is to either allow the signal to pass or you block the signal. Okay. So the filter provides that output. We use this term that filters attenuate unwanted frequencies instead of completely reject them. And that is important because a filter, right, or filters, when we use the word attenuate, what that really means is that it reduces the how should I put it now? It gradually reduces the size or the intensity of the signal, all right? So that's why we use the word attenuate. So it reduces the strength or weakens the signal, all right? So that's attenuation. The ideal operation of the signal as per this definition, the ideal operation of the signal is that it would bar all frequencies or totally bar frequencies of what is desired. However, we use the term attenuate because it's a gradual reduction. All right? There's a reduction in the strength and it is not an absolute cutoff, and that we need to keep in the back of our heads. So for the frequency, for the filter, we do have some response curves. And within those response curves, we have two areas. We have what we refer to as your stop band and your pass band. Yes? So there's a band of frequencies that we allow to pass, and there's a particular area that we call the stop area or the stop band and your pass band. So a filter can present us with two pass bands and a single stop band, or you can have a single stop band and a single pass band. And of course, since it can have two pass and a single stop, it means that it can have two stops and a single pass. All right. So the band that we're referring to here is just what is happening over that particular range of frequencies. Are we clear with that? All right. So for the pass band, for the passband, this occurs when the signals from the input to the output have very little attenuation. So there is attenuation that exists, but it is low. So the level of attenuation within the passband is low. Outside of that passband, they will fall into the stop band. Right, so that's how we are going to define it. The area that has low attenuation on the signal, that becomes our passband. And the areas where there's high attenuation, that is our stop band. Of course, we have to give filters names, and the names that we apply to them, or the nomenclature as we say, is dependent on the frequency plot. So based on the frequency response that we are going to see from our filters, then we attach a name or assign a name to them. So the names here would be your low pass filter, or your high pass, your band pass, or your band stop, or your band pass and your band stop or band reject filter. Okay. Now, one of the things we need to take note of is that since we're talking about attenuation, because we are going to be dealing with reactive elements, and we know our reactive elements, about our inductors and our capacitors, and we know that they have different responses to frequency, yes? So we therefore can determine what the output would be like by virtue of where in the filter circuit we connect the particular reactive element. And I needed to keep that at the forefront of your mind. So I may be using the same two elements within the circuit, but just by virtue of where I take the output, I can create a low pass or a high pass filter. All right? So your low and high pass filters. So going back to the nomenclature that we just spoke about, we have the low pass, we have the high pass. Yes? For the low pass and the high pass, they have a single pass band and a single stop band. And the point of demarcation, or where we separate this pass and the stop band, is dependent on what we refer to as the cutoff frequency. Right? And the cutoff frequency is that particular frequency value above which or below which the attenuation is high. So if we have the area that we have increased attenuation would represent the stop band, but the cutoff frequency separates the level of attenuation being considered. And there is that magical point that we always talk about, yes? When we're looking at resonance, what's your cutoff frequency? Because below a certain point, we're saying that that is really noise. So the useful frequencies above or below the cutoff point is what we're going to be focusing on. Now for your band pass or for your band pass filter, it has a single pass band and two stop bands. And we had said that earlier, okay? While the band reject or band stop filter, it has a single stop band and two pass bands. And we're going to be looking at these diagrams, and hopefully that will help to clear up a lot of what we're saying now, right? So the pass band or band pass filter, as well as the band stop or band reject filter, would have two cutoff frequencies, right? Because if you have a band of frequencies in the middle, which would be your band pass. If you have a band of frequencies in the middle that you allow, that would be a band pass filter. So there is a frequency below that range of frequencies, right, that you're going to reject. And there's a frequency above which, above the pass band frequencies that you're going to reject. And the same is true for your band reject filters. It has two cutoff frequencies. There's a band of frequencies, or there are frequencies below the cutoff frequency, the lower cutoff frequency that you're going to allow to pass. And there are frequencies above the upper cutoff frequency that you're also going to allow to pass. But within that range of frequencies that you're rejecting, there will be high attenuation. All right? I pause here. Any questions? Have I said anything? Or,
Sure.
yeah.
Could you remind us back what do you mean by attenuation?
Attenuation is the reduction, the gradual reduction of the strength of the signal. So it's a gradual reduction. As a matter of fact, the word attenuation, the simple word attenuation in English means to make slim. And that's what it really means, to make slim. So when we apply that to our filters, and we say where the signal is being attenuated, what it means is that we are cutting down, right? I suppose people like me need to do a bit of that right now after COVID, but anyway. So it is a reduction in strength or weakening in signal.
All right, sir.
So coming out of what the topic we just completed, in considering filters, one of the benefits of looking at transfer function is that if we have the transfer function of a filter network, it can give us both the magnitude and the phase of the output signal. All right. So if we find the transfer function, yes, for the particular filter network, we can derive from that the magnitude and phase of the output signal. Okay. So before we go any further with looking at the transfer functions, I don't want to take you to the outputs, what the output signals for your filters would look like. And these signals that I'm about to show are the ideal response curves. All right. So ideal, remember now, we're talking about cutoff. So if we say a low pass filter, that means that it will, the ideal thing is that frequencies below or between 0 up to the cutoff would not be allowed to go through. Right? Ideally, all of that at full blast. And then once it reaches cutoff, it would go to 0. So that would be the ideal output. But again, we're talking about attenuation. So it's about weakening. So for the ideal output, yes, for a low pass filter, that's what we would have. And of course, for a high pass, Are we finished with this?
Not yet, sir.
Not yet, sir.
Are we ready again?
Yes,
We have this.
yes, sir.
I just made a big boo boo. I just realized I wasn't recording the lecture. Anyway, all right. And for your band pass and band stop filters,
Sir, I don't know if you're teaching, but your mic is muted.
I how much I have said just now. Thank you very much for that. So let me go over this again. The output of the frequencies that we are going to be considering, yes, or the output of our filters, is going to be dependent on not only the element in of itself, meaning whether we are dealing with a resistor, a capacitor, or an inductor. All right, so that's important. However, we also have to take into consideration the orientation. In other words, how exactly we connect the elements. So if we had an inductor and a resistor, if I'm taking it across, if I'm taking the output, for example, across the inductor, then I have a high pass filter. But if for the same connection, if I take it across the resistor, I end up with a low pass filter. Yes. Again, with orientation, if we have an inductor and capacitor in series, the response is going to be completely different as to whether or not I have them in parallel. Yes. If I have that parallel section in parallel, as against having that parallel section in series, again, the behavior of my filter is going to change. So orientation is critically important. All right. The second point we want to make is that given that the responses are gradual and not absolute, meaning that as soon as we get to a point, we cut off, or as soon as we get to a point, we have output. Right? Since we're dealing with gradual values or gradual responses, we refer to a frequency at above or below a particular threshold. And this particular point that we refer to is our cutoff frequency. And we have been talking about the cutoff frequency since the start of the class. But, we want to delve into it a little more here. So, bearing these points in mind, one, the individual elements, whether we're using R, L, or C. Two, orientation, how we connect them. Three, we're talking about gradual values or gradual responses, gradual output, and not absolute. So we are going to therefore have to consider cutoff. So looking at each of these filters, we have to look at the elements, how they're connected, look at the appropriate response, output response, and fourthly, at what point or what frequency we have cut off. All right, so those would be the four considerations for each filter that we look at. So the first one I want to consider this afternoon is our low pass filter. All right. All right, I think just a sec. I think I'm missing a slide here. So let me make sure that okay. All right. So this is better now. So for our low pass filter, we are taking the voltage, the output across our resistor. Okay? And so if the output, and remember we said earlier that we can look at, based on the transfer function, we can get the magnitude and the phase. All right? So we have here our output across our resistor. All right? And of course, that's our input. So our transfer function be equal to V0 over Vi. We have just completed this, so we can now transfer all of this to the frequency domain, which means that we have SL and we have R. But let us, before I go there, let me just talk quickly about why this would be a low pass filter. At low frequency, we know that XL, and we know that XL is equal to omega L. Agreed? So at low frequencies, it means that XL will be small because we know that the relationship between XL and F is a direct proportionality. So at low frequencies, XL is small. Okay? So it means therefore that the voltage drop across L would also be small relative to R. So if I'm having smaller voltage drops, it means that more of the input would be seen across R. Everybody clear on that? So at lower frequencies, XL is low. Because XL is low, the voltage drop, VL, would also be low. Which means that a larger portion, if we just look at voltage divider, yes, a larger portion of the input will be seen across R. But as the frequency increases, yes, as the frequency increases, XL will be getting larger, which means therefore that a larger portion of V would be seen across L. So the output starts to get small, okay? Which is why we end up with a low pass filter. Any questions on that, or is that crystal clear? All right, now in the frequency domain, if we apply the voltage law, yes, we know that the input voltage would be given by the current times SL plus R. V in over SL plus R. So we can simplify this. So we can simplify this. And our transfer function becomes V out over V in, which is R over L over S plus R over L. Now, for those who have done, to be honest, I'm really not sure which one of the math levels, but I think it's math 3. You would have done Laplace, yes? Or you'd have done Fourier. Okay? So you would know that for your Laplace, it's a two-dimensional representation. So S is actually equal to sigma plus J omega. Okay? If we want to do the analysis in one of these two planes, yes, then meaning sigma is equal to 0. So we can and I'm so simplifying this. S would then be equivalent to the j omega. So we can look at the transfer function in terms of determining the response on the imaginary axis for omega, yes, which of course is our angular frequency. Okay, we can then simply replace our S with j omega. All right, I
Sir,
say that, yes.
can I go back over this S thing?
That's what I'm saying. It's really something that would be that requires or would be best understood if you have completed the math. I'm saying in the Laplace, for your Laplace, your S is that it's two-dimensional, yes? So the two dimensions would be a real, which is sigma, plus j omega. Those are the two planes, right? The two dimensions, okay? However, remember that we said earlier that, well, not earlier, but on Monday, that the Laplace domain is in the frequency domain. So we are transferring from the time to the frequency, okay? So we have this circuit now is in the frequency domain. And in the S domain, it is seen on, for use of a better word, two planes, the real and the imaginary. Our analysis for our filters is considering what is happening with the frequency. Okay? So I'm going to replace where I have S here, I'm going to replace it with j omega. All right? And as I said, this is your understand. If you have done the math, then it was the Laplace versus the Fourier representation. Okay, if you look back at what we had for your Laplace, where we had e to the minus st, right? For the Fourier, we would have j omega. And so I'm saying they are connected. That's just one looks at the 2D, and this is looking at one dimension, which is really on one axis. All right. So this is going to be a j omega, and that would be sigma. And then in the S plane, this would be the S plane, which then has the real, which is your sigma, and your imaginary, which is your j omega. All right. But I don't want us to focus on that. I'm saying, I said that because of what I'm going to go to next, right? Which is that for your frequency response, yes? So to oversimplify this, wherever we had S, we're going to put in j omega, all right? But remember, they are connected. It's just that we are making sigma 0 in our analysis, all right? Okay. So having said that, your h of j omega, still a transfer function, but now we are looking just on the imaginary plane, all right? The modulus of j omega, going back to what we said earlier, that once we had the transfer function would give us the magnitude and the phase. All right? So the magnitude is given by r over L, the square root of omega squared plus r over L all squared. All right, so that's the magnitude. And the corresponding angle will be given by inverse tan, or the negative of the inverse tan of omega L over R. All right. So if you have a complex number, R, A plus JB, yes, then we can find the modulus of R, and we can find theta. Okay, that's what we are doing, moving from here to here. Right? And also for that. So just note this on it. So you have the magnitude, and we have that. So let us assess how this filter will respond both in magnitude and phase. Right? That's something that we're going to be looking at. Right? Now, earlier, we said that there are a number of things that we're going to focus on. We're going to focus on the elements. We're going to focus on the orientation. Then, of course, we also have to focus on cutoff. Right? Where, at what point does it cut off? And we are going to go back to what we did in Networks 1. Right? And we are going to just introduce what we refer to as the half power points. So cutoff occurs at the half power point. Now we know from what we did in Networks 1, yes, that is true if the magnitude is 1 over root 2 times the maximum value of H. And H here, H max here, we're going to use, anyway, we're going to use per unit, yes? So H max would be 1. Right? So the maximum would be 1. So when it reaches 0.707, I'm assuming we remember all of that, right? 1 over root 2, 70.7%. It is at that point that we refer or we designate cutoff. So I'm going to make the magnitude 1 over root 2. So where the magnitude is 1 over root 2, it means that we would have reached our cutoff frequency, omega c. So note the change in the bracket for omega, not in the bracket, in the square root sign for omega. It is now omega c. All right, so here it's just omega. So this is a general expression. However, at cutoff, it's now omega c. So at omega c, at the cutoff frequency, the magnitude is reduced by that factor, or the amplitude is reduced by that factor, 1 over root 2. Okay? So if we simplify this, and our objective, students, our objective at this point is to find omega c. At what point? At what point does cutoff occur? So if we square both sides, yes, then of course I'll get a half, yes, and I'll have this squared, and of course the square root sign will disappear. All right. So if I square both sides and simplify, then I get this expression. All right. So that is 2 r over L all squared is equal to omega squared plus r over L squared. I bring this over, I get r over L squared, so I get omega c to be equal to r over L. All right. Now, for that circuit that we just looked at, what does r over L represent? Anybody? What would r over L represent?
The inverse of the time, the inverse of tau.
Time constant.
Yeah, time
Yes.
constant.
Yes. Okay. So the cutoff frequency occurs at 1 over tau. All right, we finish with this? So if you look back at your equations for omega, yes, or for the magnitude of the transfer function, we now want to sketch the amplitude. So we know that maximum is 1. Okay? We all know that. So at 0, at omega equals 0, what would the transfer function be equal to?
One.
1. All right? And that 1 would be represented by what? Oh, you get the 1.
R over L divided by R over L.
Okay, good. So it means that we would be starting out at 1. All right? Now, let's go to the extreme. If omega was infinity, then what would be the output? What would be the magnitude of the transfer function if omega is, or should I say, yeah, if omega is infinity, what would be the magnitude of the output?
0, sir.
0, all right? So it will be going down to the frequency axis, yes? Fair enough? So what that is telling us is that as omega increases, yes, we'll have a gradual reduction in the output from our filter. So we'll have here, all right, so it will be tending towards 0. And at cutoff, which occurs at R over L, yes? So this would have been at the 1 over root 2, or 0.707. Everybody comfortable with that? For the phase, at omega equals 0, the inverse tan at 0, the 0, yes? And of course, as the frequency increases, of course, we know that as the tan goes up to infinity, fair enough? So the inverse tan of infinity would be 90. Okay? So we know that at infinity, we would have come down to minus 90 because it's minus 90 inverse tan of omega L over R. So at 0, we are at 0. All right? And then there's a gradual increase going up to the 90. That's not drawn all that well, but you get the idea. And there's no kick at the end. So I've looked at the low pass filter using the inductor and the resistor. The low pass filter, because remember what, and I know I'm repeating this a number of times, but it's for good reason. We spoke about element and orientation. So I can also create a low pass filter by changing the element, changing one element, and also changing orientation. To do that, do we have this? We finish with the plots?
Yes, sir.
We can now make the capacitor and the resistor in series with each other. So I'm replacing the inductor with the capacitor. But by virtue of orientation, I am now taking the output across the capacitor. Yes? And if we use the same analysis or a similar analysis to what we just did for the inductor, yes, we know that the capacitive reactance inversely proportional to our frequency. So at low frequencies, we have Xc being high. If Xc is high, it means that we are seeing more of the output across C. So for low frequencies, we'll be seeing more output across the capacitor. Right? And as the frequency increases, it means that you're going to see more of the output across the resistor. Now, if you think about it, and if you go back to, what you were doing in high school, or possibly you may have done it in electronics here. One of the simplest filter circuit after you have done the rectification is just to throw a capacitor across the output. Yes. One explanation is that it's used to shunt, to create a short circuit for high frequency signals. Okay? And so you'll get the lower frequency. So it will be coming closer to DC. All right? So at zero, meaning a very low frequency, right? The very low frequency, you would have everything, all the output across the capacitor, which would form the output to your circuit. And of course, we want DC, which has a frequency of zero, no? So at those low frequencies, you'll see the output across the load. All right? All right. But we don't want to be stuck in that. We want to focus on it in terms of filter operation. And so at low frequency, we'll see more output across the capacitor based on what we just said. But we need to come back and look at the transfer function. Yes? So the transfer function, V out over V in, but the output is across our capacitor. So we can use a similar analysis as before. Okay. So I know I've skipped a couple steps, but since we are going through them with the inductive circuit, kind of fill in the blanks here. And as before, we know that the cutoff is equal to 1 over tau.
Sir, is it tan or tan inverse?
Minus tan inverse omega RC. Please make the correction because, of course, it's still a low pass filter, so that should remain the same. Yeah. All right. But we can make a general statement for our low pass filter. And that is, for your low pass filter, H of S is equal to omega C over S plus omega C. And for your RC circuit, it's 1 over RC, and your R over L. Okay? And we have already made the point, but put it in note form. Omega C, reciprocal of the time constant for your circuit. Okay? All right, do we have this?
Yes, sir.
Okay, thank you, Mr. Henry. All right. So for your high pass filter, again, all we are doing here is changing orientation. And if we think about the operation at low frequencies, it means that most of the output will be seen across the capacitor. At higher frequencies, because XC is now falling, yes, it means that more of the output will be seen across the resistor. So just changing the position or the element across which we take the output shifts us from a high pass to a low pass, or low pass to a high pass. All right? So for as before, the transfer function, V0 over V in. So the first thing we want to do is just to right? So in the frequency domain, again, we're using voltage divider. So that's the modulus, that's the magnitude, and the frequency. This is on 90 minus tan inverse omega RC. Okay. But as before, we have here so for the amplitude, as omega tends towards infinity, based on the equation we have for the amplitude, as if omega tends towards infinity, then it means that this will be tending towards 1. Okay? And of course, at omega equals 0, then that will be equal to 0. So we are starting from 0. Okay? Again, at our 70% line, to a cutoff. For the phase angle, 0 would be at 9. Okay? And as opposed to we're going to 0, right? The Okay? So those would be your all right. So that's it for the RL circuit, RC circuit, sorry. We don't want to look at the RL. So I'm just drawing this in the frequency domain. So we have our SL, we have R, and we are taking the output across the inductor. I trust by now you're noting the pattern. So for the RC, we're taking the output across the resistor. For the RL, we're taking the output across the inductor. And if we do the same analysis as with our low pass, and bearing in mind that the same frequency response would be true for this circuit. Just that instead of the RC, we'd have the L over R. So same analysis we did for the low pass. Yes. Cut off occurs at 1 over root 2 H max. So for your high pass filter, yes, omega C will occur at R over L. So whilst I didn't show that in the figure, we're just highlighting that fact here. And we did say earlier that the cutoff is the frequency above or below. Yeah? So the point at which it occurs, whether we're dealing with a low pass or a high pass, would be the same.
Question, sir. So this is the same for the capacitor for high and low. The
Okay.
cutoff frequency. So for the cutoff frequency for the capacitor, RC.
For the RC to the 1 over RC.
Oh, okay.
So for both high pass and low pass, yes, the cutoff will occur at 1 over tau. Tau being for the RC circuit or the RN circuit. All right. Okay. And so, as we did with the low pass, where we gave a general expression, yes, in terms of its operation, yes, where we had H of S being equal to omega over S plus omega. For the high pass filter, yes, for the high pass filter, H of S is equal to S over S plus omega C. All right, so I'm going to wrap up this evening by just introducing a couple things as it relates to using tuned circuits for filters. So far, we have just looked at having an inductor or capacitor along with a resistor. But there are filters which use a combination of inductors, capacitors, and resistors. Yes? So we want to just do the general introduction, and then we'll wrap that up on Monday. All right. So we have been talking about the orientation. Well, I think I've said that often enough, so I can leave that first point. Coming back to orientation, however, if we use tuned circuits, they can be used to attenuate undesired signal, right, or undesired frequencies. Now, in writing this, students, just as I have said in other topics, this is one of those things that I want you to use your highlighter, your reading pen, underline if you need, whatever, right? But this point is important. In writing it, just make sure you underline to highlight the importance of the point being made. In using tuned RLC circuits to attenuate, note, it is to attenuate the undesired signal frequencies. Yes. We can either connect a high impedance path in series with the signal. So if I want to attenuate an undesired frequency, so that is if I want to block, if I want to attenuate, if I want to reduce the strength, I connect a high impedance path in series with the signal. So if I want to block the signal, I put the high impedance in series. All right? Or I connect a low impedance path in parallel with the signal. So this is about attenuation. So if I want to attenuate a signal, right, meaning I don't want it, I can put a high impedance path in series or a low impedance path in parallel, which is exactly what we're doing with the single elements. Yes, but I didn't present it in this fashion. I'm using this particular way of explaining it to introduce the use of tuned circuits. Okay, but if you look back at the single elements, that's exactly what we're doing. For your high pass filter, when we're using the capacitor, yes, which signals did I want to attenuate? Low frequencies. Everybody agree with that? So I'm attenuating low frequency. So if I'm attenuating low frequency, it means therefore that I'm going to connect the capacitor in series because it would attenuate low frequencies. It would block low frequencies. It will give me a high impedance path to low frequencies. Yes? But when I'm using the RL, yeah, remember now, it's the low frequencies the high frequencies that I want to pass. So I want to attenuate low. I put the low impedance path in parallel. So I want it to divert, so to speak, the low frequencies. So I put the inductor, which has a low impedance to low frequencies in parallel, because that is what I want to attenuate. So I'm doing that using the tuned circuits, right? I'm going to do that using the tuned circuits. And so in wrapping up this evening, these will be your final diagrams. So these options provide for the creation of 3 standard configurations. We can either have an L-type configuration, a T configuration, or a pi configuration. All right, so those are the 3 standard configurations that we are going to be looking at. While you're doing that, I'll just take the register. So Adams? Adams has been absent all week. Okay. Smart.
Yes, sir.
Okay. Blackwood.
Yes, sir.
Okay. Brown. Beresford. Absent. Bosu.
Yes, sir.
I heard Mr. Campbell earlier. Ms. Chen.
Yes, sir.
Clark.
Sir.
Crosdale.
Present, sir.
Darby. Davis. Dona. Ellis.
Here, sir.
Ferran.
Here, sir.
Forrester. Grant.
Yes, sir.
Gray.
Here, sir.
Jeffrey.
Here, sir.
Johnson. Yes. Johnson, you still there?
Yes, sir.
Kamika.
Here, sir.
Lewis. Nicholas.
Here, sir.
Lynch. McFarlane, yeah. Merritt. Montague.
Yes, sir.
Nevers. Phillips.
Here, sir.
Port. Ramsey.
Here, sir.
Ready. Thomas, one eye. Watson.
Yes, sir.
Wilson. Well, so Wilson could not be here. All right. Oh Lord, I don't believe that does happen. Okay, so you have these orientations. Yep. So we'll pick it up from here on Monday, where we'll delve into a lot more detail in terms of the operations and how and that will lead into the design that you have to do for your assignment. All right. So if there are no questions, that's it from me for today.
Sir,
Yes.
question. I know probably you won't answer. In regards to the grade that we obtained, the grade that we obtained for this test on Friday, sir. When are we going to see those, sir?
You'll have them tomorrow. You really should have gotten them already. So you'll have them tomorrow.
Okay, sir, thanks.
Then why wouldn't I have answered that? You should have had them from Monday. You know? So it's tardiness on my part. But,
that's okay, sir.
All right. So you'll have them, your grades tomorrow. Any other questions? All right. So that's it for today. Have a good evening, everybody.